Tieres shunting going on over there. Ich will go ahead and see was es ist all about. Stup tis recht now. Tis ist so stupid. Have you lost your name? Grow up. Tis is no longer Jurassic. Tilly, don't listen. It's like talking to a spanner. You could hurt yourself. Ouch. That was to be expected. Everybody inside. Tis was extremely stupid. Ich hope you learn it your lesson. Ich do not have high hopes für die Schickais.
Hello! Well, in this episode of Finnogric Machining, well, it's going to be the first episode of a series where I'm making a knurling tool. Well, and this time it's English, and there will be several other languages used on the way. But let's start this with an English-speaking episode. First of all, I purchased these things. If I take them, some of them out from there, like that, they are like that. These are knurling wheels. I don't know the exact term, what it should be, but I call them knurling wheels. The outer diameter is 15 millimeters, and then the hole is 4 millimeters, and the width of those wheels is 6 millimeters. So they are not that big. Lucky for me. I don't usually make things that are really huge. Well, there are some exceptions. First I will discuss a little bit of different geometries involved with knurling. There are, at least that I know, 3 common types which are like deforming the metal, and then there are some knurling tools that are cutting the knurls. The ones that actually push the material and make the knurl, the geometries are a little bit easier. In the next animation I will talk about those 3 different types of geometries that I know of, and one of them is selected for this project. So let's start with that animation. First, let's see what happens to the workpiece when it is knurled using the deforming process. Usually the knurling is made on a round workpiece. The workpiece is rotated and a knurling wheel is pressed against it. The surface of the workpiece will be deformed by the knurling wheel. The resulting knurl depends on the type of knurling wheel used. The most common knurling wheel types are straight and diagonal. The straight knurling wheel creates a straight knurl, whereas the diagonal wheel creates a crosshatch knurl. Since the material is displaced and not cut away, the workpiece diameter will grow slightly. Knurling by deforming can only be applied to materials that can be deformed. Materials that are hard or are crumbly cannot be knurled by deforming. Also, if the material is very elastic, it cannot be knurled this way, as it will bounce back to its original form. Materials that can be knurled by deforming include most unhardened steels, most aluminium alloys, copper, brass and most bronzes. Rubber, hard steel, most plastics and some bronzes cannot be knurled by deforming because they are too hard, too elastic, or crumble under the knurling wheel. The simplest form of knurling tool pushes the knurling wheels against one side of the workpiece. Since the force required to deform the material is considerable, the workpiece and the lathe need to be really sturdy. If the workpiece is not sturdy, it will bend and there will be no knurl, or the quality of the knurl is poor. If the lathe is not up to the task, the spindle bearings may get damaged. Although this type of knurling tools are usually affordable, I don't recommend them because they can damage the lathe or ruin the workpiece. A much better approach is to push the knurling wheels against the workpiece from opposing sides. The two knurling forces will cancel each other and there will be only negligible forces to spindle bearings or to the workpiece. Two common variants exist of this type of a knurling tool. In the first variant, the knurling wheels are attached to the ends of two arms that do not share a common pivoting point. This variant must be adjusted at the precise center height for the knurling forces to cancel each other. It is also very sensitive to any eccentricity of the workpiece. The other variant, also known as scissor type, is similar, but the arms where the knurling wheels are attached to share the same pivoting point. This variant is quite immune to center height or eccentricity of the workpiece. For these reasons, this is the variant I am going to make in this project. This is the bar that attaches the knurling tool to tool holder. Both halves of the scissors rotate around this shaft. The shaft is attached to the bar using two M6 cap screws. The lower half of the scissors is made of two parts that are thick welded together. In the rod of the lower half of the scissors, there is a dimple where the lower part of the tensioning system can rotate. This lower part has a M10 thread so that the upper part can be jacked up by rotating the lower part. The upper half of the scissors is otherwise identical with the lower half, but it has a round groove instead of a dimple for the tensioning system. Both halves of the scissors are held in place with a hook and a M6 cap screw. These two sleeves keep the two hardened pins for the knurling wheels in place. This knurling tool is designed for ease of change of the knurling wheels. The two knurling wheels are held in place by hardened pins cannibalized from a needle bearing. These hardened pins are held in place with the two sleeves that slide over them. No tools are required to change the knurling wheels. This knurling tool can knurl diameters ranging from 0 to 41 millimeters. When adjusted properly, this tool presents very little forces to the lathe or the workpiece. This tool squeezes the knurling wheels across the workpiece instead of pushing them from one side only. Since both halves of the scissors share a common pivoting point, tool height adjustment has no impact on knurling forces or the quality of the resulting knurl. Okay, now this workpiece was cut with a bandsaw. There is one edge that is properly machined, and the rest of the surfaces are really bad. Not bad, but nothing that one could actually attach something into. I want to get rid of this. Okay. Yes. This is copper foil. Copper foil. Okay, it should be enough. It is. I will actually shorten it a little bit. This is 0.1 millimeter thick copper foil. I just use it to even out the roughness of the surface so that my vise can get a good grip on that one. Yeah. And now, suitable parallel under there. Let's try with 24 millimeters first. Should be 24 is too much. So 20 millimeters then. This is a roughing end mill. It's now 14. So 22 millimeters is a proper one. I don't remember the height of this vise, so I always seem to be testing it. I will just put this copper thing around it like that. I will actually knock it down a little bit. Let's see if I can do that. Yeah, switch on this thing. Well, at the moment we have here in the workshop we have 15 degrees Celsius. It's cool. And outside it's at the moment 18 degrees minus side. So a little bit Arctic air here. And this one doesn't run very fast. Let's see about the speed. That's a little bit too slow. That's okay. Yeah. And then I switch on the feed. It takes a little bit some time to warm up. So I let this run like this a while because it has been really cold here. So it will, well, I actually should oil it. Lubricate it. These two oil nibbles here push the oil back, way back in there. And these are really, oh wow. Once I get the oil from this can, okay, now it went there. Next squeeze, 2 squeezes on each. That's good. And then these 2 oil nibbles are for the spindle bearings. And these need only 1 squeeze each. Yeah. Oh yeah, it starts to warm up. How high was it? Well, it's 32 millimeters. So, and our goal is 14. So I can take 15 millimeters in the first pass, really. And then there is an oil glass here under. I can look at it and you can see when the oil starts dripping there, then it's ready to go. But not before that. So the feed rate, let's try 20 millimeters per minute per, maybe, yeah. I will increase that if it's too little. And then let's scratch this surface a little bit. Huh. Wow. Okay. now it scratches, and I can now take 15 millimeters. It's 10 turns from this shank. 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow, that seems like a lot. Let's take a little bit less first. That was quite a lot. So let's take 6 millimeters. So 1, 2, 3, and 4. That's 6 millimeters now. Let's see how it reacts on it. Yeah, no trouble at all. Good. Well, this needs cutting oil. This one you cannot run without. So, I will bring you nearer so you can see more exactly what this does. Well, yeah. Well, okay, I think we are ready to go with this one. So, the feed is dripping the oil system, and now let's see. And this really needs cutting oil. It doesn't work without. So I put the oil, cutting oil, on the shaft, so it slowly goes down. And remember, this is tool steel. This is nothing to do with mild steel. This is hard. Well, the chips turn blue because the workpiece heats up. There you are. 6 millimeters. Wow. And now I will get rid of those. I don't want to. I do it like this. Try to get them out from here. Like that. Whack. Next layer. Okay, now again trying to get this out from here without this end mill the chips it produces are not sharp, and that's really nice. Well, this is the last pass here, so, and after this I swap another type of end mill here. This is really roughing. So, it's about 130 revolutions per minute, and the feed rate is 30 millimeters per minute. And it cuts really nice. The cut depth here is 6 millimeters, so, and this is quite hard tool steel. Okay. Let's take it. Oh, here. Okay. Now I collect the chips. Try to collect them at least, most of them. Like that. And now we don't need this cutting oil anymore, because I'm swapping over to an carbide end mill, and that will be a little bit, it can be run without cutting oil. Okay, so now we have a different end mill here. It's an end mill with inserts. So, well, and this is also special. It rotates into the wrong direction, like this way. Luckily my machine has the ability to rotate in both directions. So, well, let's go. Actually, I'm not satisfied with the quality of this surface. Well, no, it's rough. I'll try another type of a solution here, another cutter. Maybe I can get a better surface. That one is not good. Okay, now we have a different tool here. It's a boring bar and it acts like a fly cutter. Oh yeah. So, and the parameters are exactly the same. So 600 RPM, but the depth of cut is smaller. I will also increase a little bit of this feed. So there we go. Wow. Oh, I ruined it with this. But, oh yeah, it's totally smooth. Yeah, this is good. Okay. So now I'll just turn it around a few times and well, I will do off the camera the finishing of all the other three surfaces. Now, drilling two 6mm holes all the way through. Well, I run this about 400 revolutions per minute and feeding by hand, I believe. Yeah, there we go. Well, and the more observant ones of you probably noticed that I run this dry. And the table x-axis was locked, so 20mm. It's about there. Now I'm trying something different. I'll try to power feed this one. It seems like it could work with power feed. But first I will You can drill a hole quite accurately in a place by starting it very carefully first. There you are. And now we can go. Let's see. Power feed 17 millimeters per minute. Oh yeah, this was fast. Way faster than and easier. Okay. Yeah. But usually I don't like to use power feed with drilling because it can be really really something. Okay. So here are the chips. Yeah. And now I will replace this one, this drill with a 10 millimeter end mill, and then I drill a recess here, mill a recess here and here. So now it's on place for this hole, and then I just need to move to that hole and do the same thing there. But I'll come back when I have the appropriate tool in there. Okay, this is 10 millimeter end mill carbide, and I will now make a recess there. It should be 6 millimeter deep, but I will make it 7.5 millimeters because it is exactly 5 turns on the handle. Yeah. Okay, so let's go. I have to feed this manually. And this is running at the moment 600 RPM. And yeah, okay, let's go. So that's 1 turn, 2 turns, 3, 4, and 5. There you are. Very nice recess. Oh man, a lot of this dust. These are not chips, this is just dust. And now, because the backslash is from the direction of backslash, how I have done it, is when I move from here to there. So now I need to go past the hole and then adjust the... Let's first go past it. Not that much. And then I approach it from here. There it should be right there. Yeah. And now the same story with this one. Let's see if my zero is in place for this one. It should be, but you never know. Next zero then. That's the zero. Yeah, okay. Now, 5 turns. 1, 2, 3, 4, and 5. It makes horrible sounds. Well, more dust. Okay, we have the recesses now there. This should be good for M6 cap screws. Yeah, oh man, these look really nice. And they are just like I estimated. This, I'll show you. When this is put into a tool holder like this, so this side goes back there, like that. So actually the only, this surface here doesn't need to be that exact. So yeah, it fits really nicely there now. Okay. Well, it should. Yeah. Well, I have been thinking about that hardening of this, and this is pretty hard without hardening. So maybe I leave it alone. Just make jam first there, and then that's ready. It's a very simple operation. Oh yeah. So that was it. Sorry, this time I didn't make a lot of machining. Just a very simple part, and that's it. Next time we will make a lot more, because we are going to make some of the, the pivoting point for this thing, and it might as well be a simple one, but on the other hand, these episodes become a little bit shorter that way. Not that I would like, I usually like to make very long episodes, but maybe shorter ones would be better. Okay, so in the next episode we will be making more parts for this one. Then about the drawings, because the drawings will evolve while I'm making this. I have done complete drawings, but there may become corrections to them. So therefore, if you want to have those drawings, they will be incomplete in a way that they might not reflect the end result. But after the last episode of this series, they will. So, what more? Maybe just bye. Okay, see you later.